Dear students, today we'll see some multiple choice questions on the topic resonance. So let's start with today's topic, that is DCET, Communication Systems Part 4. And in Part 4 we will see questions on resonance. So let's start with the first question of this part. Question number 61. Consider the following statements. When a series RLC circuit is under resonance, the first statement is a current is maximum through R. That is true. At series resonance, we have minimum impedance. Impedance will be only R and the current flowing will be maximum. Second statement is magnitude of the voltage across L is equal to that across C. That is also true because XL is equal to XC. That is reactance of inductor is equal to reactance of the capacitor. And the third statement is the power factor of the circuit is unity. That is also true because the phase angle between voltage and current at resonance will be 0 because they will be in phase and cos of 0 is 1. So the power factor of the circuit is unity. So out of this, all the three statements are true. That means which of the statements are given are correct. Then the first option, that is option A, 1, 2 and 3 will be the right answer here. So here you can see the theory behind it. A resonance occurs when reactance of inductor is equal to reactance of a capacitor, that is XL is equal to XC. At resonance, the impedance of the circuit is equal to the resistance value as Z is equal to R. At low frequencies, the series circuit is capacitive as XC is greater than XL. This gives the circuit a leading power factor. This is important. At low frequency, capacitive reactance is high. At high frequency, the inductive reactance, that is XL is greater than XC. This gives the circuit a lagging power factor. The high value of a current at resonance produces very high values of voltage across the inductor and capacitor. Next point, since net reactance is zero, circuit becomes purely a resistive circuit and hence the voltage and the current are in the same phase. So the phase angle between them is 0 and therefore cos of 0 is equal to 1. Therefore power factor is unity 1. So here you can see for the first question, the option A, that is first statement, second statement and third statement are correct. So 1, 2 and 3 are correct. So option A is the right answer. Then we'll go to the next question. Consider the following statements with respect to a series RLC circuit under a resonance condition. The first statement is all the applied voltage appears across R. Second statement is there is no voltage across either L or C. Third statement is the voltage across L and C equal to the maximum values. So out of this, at a resonance, a condition, the first statement which says that all the applied voltage appears across R is right. So here the first statement only is correct. The second and third statements are not correct. Therefore, out of this, option A is the right answer. One alone is correct. So here you can see some theory behind it. Inductive reactance XL is equal to a capacitor reactance XC at resonance. Total impedance of circuit becomes minimum, which is equal to R, that is Z is equal to R. Circuit current becomes maximum as impedance reduces. I is equal to V upon R. Voltage across inductor and capacitor cancels each other. So voltage across resistor VR is equal to the applied voltage, that is the supply voltage V. Since net reactance is zero, circuit becomes purely resistive circuit and hence the voltage and the current are in the same phase. So the phase angle between them is 0, and because the phase angle between voltage and current is 0, cos 0 is equal to 1. So power factor is unity. So here, as we have seen earlier, option A, that is the first statement, all the applied voltage appears across R, is correct. Then we'll go to the next question. A series RLC circuit will have unity power factor is operated at a frequency of what? So here we know at series resonance, the resonant frequency is given as Fr is equal to 1 upon 2 pi root LC. Okay. So here A series RLC circuit will have unity power factor at resonance because voltage will be in phase with the current, and therefore the cos zero of the, that is, there is no phase or difference between voltage and current, so it is zero angle. So cos zero is equal to 1, so it is unity, and this happens at a frequency that is a resonant, that is resonant frequency for that circuit. So here 1 by 2 pi root LC means option D is the right answer here, 1 by 2 pi root LC. So here you can see option D, 1 by 2 pi root LC is the right answer because it is the expression for the resonant frequency for series resonance. Then we'll go to the next question. Question number 64. A circuit with a resistor, inductor and capacitor in series is resonant of F naught hertz. If all the component values are not doubled, then what is the new resonant frequency? So here we know that the resonant frequency for series resonant is given as 1 upon 2 pi root LC. Okay. Now if we double the component values, so component values are L and C, so this equation will become 1 upon 2 pi root 2L 2C. So the L and C components are doubled. So this is nothing but 1 upon 2 pi root 4 LC. Now root 4 is nothing but, we can take it out as 2 because 2 into 2 is 4. So this is nothing but 1 upon 2 into 2 pi root LC. This is nothing but 1 upon 2 of resonant frequency. This is nothing but Fr by 2, or if you denote a resonant frequency as F naught, then you can write it as F naught by 2. So here, if all the component values are not doubled, the new resonant frequency is F naught by 2, that is option D is the right answer here. So here you can see F naught by 2, that is option D is the right answer. Then we'll go to the next question. Question number 65. In a series RLC circuit at resonance, the magnitude of voltage developed across the capacitor is always zero or can never be greater than the input voltage, can be greater than the input voltage, however, it is 90-degree out of phase with the input voltage, can be greater than the input voltage and it is in phase with the input voltage. So here 90-degree out of phase with the input voltage and it can be greater with the input voltage. That is option C is the right answer because we are speaking about voltage across capacitor at resonance. So here option C is the right answer. And for that we can see the theory behind it is series resonance RLC circuit is also called as voltage magnification circuit because of the magnitude of voltage across the inductor and the capacitor is equal to Q times the input sinusoidal voltage V. So here option C will be the right answer. The voltage across a capacitor can be greater than the input voltage. However, it is 90-degree out of phase with the input voltage. Then we'll go to the next question. A coil having an inductance of 0.5 henries and a resistance of 60 ohms is connected in series with a capacitance of 10 microfarad. The coil is connected to 100-volt AC supply. What is the source frequency and the current flowing in the circuit under resonance? Now this is the problem asked here. So here we have to find the source frequency, that is frequency of resonance, and then we have to also find the current flowing through the circuit. So here we will start with what is given. So here you can see, so here what is given is inductor is given. Inductor is nothing but 0.5 Henry, 0.5 Henry. Resistance is given as 60 ohms. Then a capacitor is given as 10 microfarad, and then voltage is given as 100 volts. Okay, so these are the things given. Now first we can find out the resonant frequency. Resonant frequency is calculated as, you can take it as FR or F naught. So FR is equal to 1 upon 2 pi root LC. This is nothing but 1 upon 2 into 3.14 into root of inductor is 0.5 and capacitor is 10 microfarad, so 10 into 10 to the power of minus 6. So if you solve this, if you evaluate this, you will get Fr is equal to 71.21 Hertz. So here you can see 71.21 Hertz in C option and in D option. So any one of this will be correct. We'll just go to find out what is the current in the circuit. So to find out our current in the circuit at a resonance, you can see that our current is equal to V upon R. So current is equal to V upon R. So V was nothing but 100 volt upon R is nothing but 60 ohms. So V upon R 0 will get. So it will be 10 upon 6, and 10 upon 6 is nothing but 1.67 amperes. So here 1.61 amperes. This is the right answer. So option D is the correct answer. 71.21 hertz and 1.67 amperes. Then we'll go to the, so here you can see option D is the right answer here. Then we'll go to the next question, question number 67. In a series RLC circuit, the maximum voltage across the capacitor occurs at what frequency? Now we know that the reactance of the capacitor will be more for the frequencies below the resonant frequency, and therefore maximum voltage across the capacitor will occur below the resonant frequency. So here out of these options, option D will be the right answer, below the resonant frequency. So here you can see option D is the right answer, below the resonant frequency. Then we'll go to the next question. In a series RLC circuit, the maximum voltage across the inductor occurs at frequency of what? So because the capacitive voltage is maximum below the resonant frequency, the inductive voltage will be maximum after the resonant frequency. So the option B, that is just after the resonant frequency, is the right answer here. So here you can see option B, just after the resonant frequency, is the right answer. Then we'll go to next question. Q factor of a series RLC circuit possessing resonant frequency 10 Hz and bandwidth as 5 Hz is given as how much? So here you can see, if you see here, the resonant frequency F0 is equal to 10 Hz and bandwidth is equal to 5 Hz. Now we have the expression for quality factor, that is Q factor. Q is equal to F0 upon bandwidth. This is nothing but 10 upon 5. This is nothing but 2. So here option B will be the right answer here, 2. So the quality factor Q will be 2. So here you can see option B is the right answer, 2. Then we'll go to next question. When Q factor of a circuit is high, then the options are power factor of the circuit is high, impedance of the circuit is high, bandwidth is large, and none of this. So here out of these options, option B is the right answer here. Impedance of the circuit is high because the Q factor of the circuit is high. Okay, so it is impedance which goes along with the Q factor. So option B will be the right answer. Impedance of the circuit is high. So here you can see option B is the right answer. Then we'll go to next question, question number 71. In a series resonance circuit with increase in L, option A is resonant frequency will decrease, bandwidth will decrease, Q will increase, or all of the above. So out of these options, if you see, resonant frequency will decrease because we know that resonant frequency is equal to F is equal to 1 upon 2 pi root LC. So as L increases, the resonant frequency has to decrease. So this is correct statement. And bandwidth will also decrease because our resonant frequency is going to decrease. Okay, so here you can see the it will affect the bandwidth also. The inductance increase will also decrease the bandwidth, and it will also increase the Q factor because Q is equal to omega L upon R. So if L increases, Q increases, so this also increases. So all of the above is the right answer here. So here in this question, in a series resonance circuit with the increase in L, all of the above things take place. That is, a resonant frequency will decrease, bandwidth will decrease, and Q will increase. So here you can see option D is the right answer, all of the above. Then we'll go to the next question, question number 72. Which of the following will not be affected due to change in R? Options are bandwidth, option B is Q factor, option C is resonant frequency, option D is none. So here option C will be the right answer because resonant frequency is dependent on L and C. So 1 upon 2 pi root LC. So which of the following will not be affected due to change in R is resonant frequency. So C is the option here. So here you can see option C is the right answer. Then we'll go to next question. Change in circuit voltage will affect resonant frequency, Q factor, current or bandwidth. So change in circuit voltage will affect the current because voltage is directly proportional to current. So change in circuit voltage will affect the current. So option C is the right answer here. So here you can see option C or current is the right answer. Then we'll go to next question, question number 74. So here, higher the Q of a series circuit, narrower its. So what becomes narrow, whether it is pass band, whether it is resonant curve, whether it is bandwidth, or all of this. So here, pass band, resonant curve, and bandwidth all means the same thing because if for a resonant circuit, if you see, now this frequencies, now this is for your current and this is for frequency. This is 0, say. This will be the graph and this will be your resonant frequency and this will be your bandwidth f1 f2. Okay, so this is your bandwidth. Now this is the curve, this is the resonant curve in which we have pass band, we have bandwidth. So higher the Q of a series circuit, then its bandwidth or its pass band or its resonant curve will become narrower. So this will become narrow as the Q factor goes on increasing. Okay, so this can become narrow. So all this pass band, resonant curve, and bandwidth, everything becomes narrower. So all of these is the correct answer. Option D is the right answer here. So here you can see option D, all of these is the right answer. Then we'll go to the next question. An RLC series circuit has F1 and F2 as the half power points and F0 as the resonant frequency. The Q factor of the circuit is given by what? Now we know the Q factor of the circuit is given as resonant frequency, okay, a resonant frequency upon the bandwidth, okay. So resonant frequency upon the bandwidth. So half power points, if we take a bandwidth F1 and F2, so it is F1 minus F2. Okay, so here F0 upon F1 minus F2 is the right answer. So here you can see option C is the right answer, F0 upon F1 minus F2. The Q factor of the circuit is given by F0 upon F1 minus F2. So here you can see option C is the right answer. Then we'll go next question. Resonant frequency FR of a series RLC circuit is related to half power points, half power frequencies F1 and F2 as, okay. So in this, resonant frequency is given as F1 plus F2 upon 2. So here, if you see the bandwidth, okay. So here, if you are having the curve between current and frequency, so here if you see this bandwidth, okay, so here the bandwidth say is f1 and f2, f1 and f2. So if you take f1 plus f2 upon 2, you will get the resonant frequency fr. So here option A is the right answer. f1 plus f2 upon 2 will give the resonant frequency fr. So here you can see option A is the right answer. Or then we'll go to the next question. An RLC series circuit has F1 and F2 as the half power frequencies and FR as the resonant frequency. Then the selectivity of the circuit is given as what? Now we know that a quality factor was given as resonant frequency upon a bandwidth. That is, you can take it as F2 minus F1. Now selectivity is nothing but a reciprocal of quality factor. This will be nothing but bandwidth upon resonant frequency, F2 minus F1 upon FR. So here Out of these options, option C will be the right answer here, F2 minus F1 upon Fr. So here you can see option C is the right answer. Then we'll go to next question. A parallel resonance circuit can be employed. Option A is as a high impedance. Option B is to reject small band of frequencies. Option C is to amplify voltage. Option D is both A and B. So out of these options, option D will be the right answer because both A and B as a high impedance or also to reject a small band of frequencies. It is used. So parallel resonance circuit can be employed for both A and B options. So option D is the right answer here. So here you can see option D is the right answer. Then we'll go to next question. A resonance curve for a series circuit is a plot of frequency versus current. So option A is the right answer here. It is a plot of frequency versus current. So here option A is the right answer. Then we'll go to the next question, question number 80. Selectivities of different resonance circuits are compared in terms of their options are impedances, reactances, frequencies, and bandwidths. Obviously, selectivities of different resonance circuits are compared in terms of their bandwidths. So option D is the right answer here, bandwidths. So here you can see option D is the right answer. That is, selectivities of different resonance circuits are compared in terms of their bandwidths. So option D is the right answer. Thank you, students.